Hello everyone, welcome to lecture 48. Today we shall continue our discussion on bipolar RF devices. If you recall, in the last lecture we concluded with the collapse of the current gain for compound semiconductor devices and how the beta, the gain of HBTs and silicon BJTs have a fundamental difference with respect to temperature. And today we will start about compound semiconductor high frequency, the cutoff frequency, some of the basics. We will look at their fabrication and then we will move to silicon germanium based HBTs. Okay. So, over to the whiteboard here. So, this was the conclusion, that was the concluding part of lecture 47 where we talked about the collapse of the current gain. Just to recap that once again, because it is very important in the context of multi-finger devices, and if you have several fingers, essentially what happens is that although they may be identical, one finger will, and they carry a lot of current. So, one finger will start becoming warmer slightly than the other fingers, and if you look at the current voltage characteristics, these are all diodes. So, you have a behavior like that. So, the moment one finger becomes slightly warm, its turn on actually slightly reduces. So, it will look something like this maybe. Okay, its turn on slightly reduces, and because it has become warm, this particular finger for instance, its turn on has become slightly lower. So, it will start conducting more current, slightly more current, and because it is starting to conduct slightly more current, it will become more warm. Because it will become more warm, it will again shift little bit. So, eventually what happens is that this finger has a positive feedback in terms of the raise in temperature, lowering of the turn on and increase in the on current. That is a positive feedback, and so eventually all the fingers, the current will be sucked away to this finger, and this finger will alone carry all the current, and that basically deprives other fingers from the current carrying capability. And so, if you plot the output characteristics, it suddenly drops. This is the collapse that happens. Okay. This part, which is the NDR, is at that point this phenomena has not yet started, but both this negative differential and this the collapse of the current gain, the origin is the same, which is basically the decrease of the current gain with temperature. Okay. Except that in the NDR part, because of the decrease in the current gain, your current is decreasing. At one point suddenly the one finger will have this dramatic increase, the positive feedback in terms of increase in current, increase and the lowering of the turn on voltage, and that leads to this collapse. Okay. And we talked about how the emitter ballast, if you have an extra resistance that you put in the emitter, then it will essentially try to reduce or mitigate this effect. It is called ballast, and then you can actually bias this device out of this collapse by coming again to this part, and then it will be fine. But unlike in silicon BJT, where if you do not take proper precaution, it will basically have a thermal runaway and it will completely destroy the device. Okay. So, now if we look at a compound semiconductor high frequency figure of merit, and of course the basic premise remains the same whether it is silicon bipolar device or a compound semiconductor device. Essentially the time that the electrons will take to reach from emitter to the collector is essentially the total transit time, and that will dictate your cutoff frequency. Of course it is 1 by 2 pi the transit time. Okay. So, there is an intrinsic delay of course, and then there is this extrinsic delay because there are all these extra parasitics that are there, right. So, the total delay will be a combination of both the extrinsic and intrinsic delays, but the basic factor to keep in mind is that the time is essentially RC. So, you basically try to reduce all the resistances, you try to reduce all the capacitances, and that will help you reduce your transit time, and that will help you increase your cutoff frequency. That is the basic mantra here. So, you can see that there are different components of delays of course. If you look at the expression, we can go one by one. So, this is your base collector capacitance charging delay. So, this term represents your base collector junction capacitance or depletion capacitance, because your base and collector is reverse biased. So, you have a large depletion with there, giving rise to a base collector capacitance. It depends of course on the area, it is very critical, we will come to that later, but Re is you can think of it like the source resistance in an FET, but here it is an emitter resistance, this is the collector resistance, and this is the RC delay corresponding to the base collector capacitor charging and discharging. Okay. Now, this is the emitter base forward biased junction capacitance, which could be very small in general. There is also a diffusion capacitance actually, which is basically the emitter base junction is forward biased. So, I have told this many times that Gm times tau f gives you the diffusion capacitance of the base emitter forward biased junction. Okay. And the base emitter forward bias junction giving rise to diffusion capacitance can be significant. The diffusion capacitance can be actually a very critical factor that slows down or that reduces the FT. So, in principle the FT of a device of an HBT could be very, very high, but in reality it is not as high as you may expect it to be, because the diffusion capacitance can become significant. It is a forward bias junction. So, there is in the emitter base junction, you have this minority storage in the base, that's and also the minority storage in the emitter. This minority storage gives rise to this diffusion capacitance in a forward bias PN junction, and that could be significant. Okay. One thing which I may not have maybe mentioned while I was talking about the base collector capacitance here, and maybe I can change the color here, is that this component that I am talking about is actually RE plus RC are the excess resistances or the parasitic resistances that are coming out, or you can say the contact resistance and everything for the emitter and the collector, which means this term actually is the extrinsic, or you can say the excess resistances plus the contact resistances, whatever the extra parasitic resistances are there in the collector and emitter, those times the total base collector capacitance. So, this is not so much as the intrinsic base collector junction depletion capacitance, that actually is captured by this quantity, which is your KT by QIC into this junction, the base collector junction capacitance. So, this is the intrinsic base collector charging discharging capacitance, which is intrinsic to the device. This is happening just right here, the base collector depletion. Okay. This particular term, okay. This particular term is more about this, the side, the resistances in the collector, okay, the contact resistance in the collector, the contact resistance in the emitter. So, this part is essentially representing this, okay, and the intrinsic delay that is happening in the below the emitter in the actual device, the intrinsic device, this is the base collector capacitance, okay, this is the base collector capacitance which is intrinsic, okay, the intrinsic capacitance base delay, okay. So, there is a base collector intrinsic capacitance charging delay, there is a base collector of course extrinsic charging delay. This component is the intrinsic base emitter forward biased junction capacitance. However, the diffusion capacitance in the forward bias can be a significant factor. Now, there are two more terms, and that is this and this. So, what are those terms? This term actually is the base transit time, this is the base transit time. What happens is that you have a minority charge storage in the base. So, how quickly are you basically flushing the charge out? So, essentially the charge stored in the base, I told you maybe in some classes before, divided by the current, the collector current that clears the charge or flushes the charge out, that is your base transit time. You can also think of it as some kind of charge is stored in the base and not in the base, in any material. If you have some charge storage and you are clearing the charge with some current, then essentially that ratio between the charge storage and the current that is clearing the charge is the time taken to clear the charge. Okay. So, this is the base transit time, and it depends as a square of the base width. This is the neutral base width, remember, and this is the diffusion coefficient of the carriers in the base. This nu that shows here, it is typically 2, but it could be also slightly different from 2, 2.5 or 3 in depending on the scaling of the device and other factors here. Okay. And then this X depletion by actually 2V set is the base collector has a large depletion rate. So, this is base, for instance, this is collector, but this is a very large depletion, reverse bias depletion that is happening at the base collector, that is also blocking the base collector voltage. So, an electron will take certain time to actually travel across the base collector depletion region, and because the field is very high, the electrons are traveling at velocity, saturated electron velocity. So, if the thickness of this depletion region is x depth, so the x depth divided by the velocity of saturation of electron should give you the time taken by electrons to travel across the base collector depletion region. However, this is a space charge region which is depleted of carrier, and whenever electrons or any carriers are traveling through a space charge region, then there is a factor of 2 here. There is a separate derivation for why that factor of 2 comes, which we are not going to discuss here, but just remember that whenever you have a space charge region and your carriers are traveling at a certain velocity, you have to add an extra factor 2 in the denominator to capture the total time that electrons take to cross across the space charge region, okay, because it is depleted of charge. So, the electrons that is traveling is in a way dictating the field as it travels. So, the derivation comes from that, and this is the total expression for the cutoff frequency in very highly scaled devices, where you can minimize many of these parameters. Also many of these parameters become very critical. There is one more delay term that comes, which is often ignored in traditional HBT, and which is basically the depletion, sorry, not the depletion, the base, the intrinsic, or I would say the the neutral base width divided by the velocity of saturation. So there is a base, I told you there is a charge in the base, you are flushing out the charge, and that is why this term comes here. However, when the electrons exit the base towards the collector, the electrons are exiting from the base towards the collector, there is an additional delay that people capture with depletion width not depletion, sorry, the base neutral base width divided by the velocity, which is the saturation velocity. That ratio gives you the time the electrons take to actually exit the base. That quantity is typically very narrow, but sometimes it can matter. Okay, so just keep that in mind, please. So this is the overall picture of the emitter, I mean the HBT delay. Okay, the total HBT delay. Essentially what is happening is that if I represent it pictorially, you have an emitter, you have a base, and then you have a collector, and what is going to happen here is that you have a small, sorry, you have a small depletion on here, and then you have a large depletion here. Okay, an electron that is starting from emitter, how long does it take to reach the collector here? That is all the total delay is. So there is some charging delay here, there is some charging delay here, there is some transit delay here. Okay, there is some diffusion capacitance corresponding to this, and then there are some extrinsic delays, which are this, the parasitic delays that are happening. So that in a nutshell captures the total cutoff frequency, I mean the transit time, and that is an important thing to keep in mind here. So then of course beyond that we also have that relates to the cutoff frequency, but then there is also Fmax, which is the the oscillation frequency, the maximum oscillation frequency that we have talked about. And just like in an FET where Fmax goes as Ft divided by the gate resistance, something like that. So similarly here, instead of gate resistance you have base resistance. The gate is equivalent to base here. So you have a base resistance and of course the base collector capacitance. So if you have to increase the Fmax, you need to really reduce the base resistance. The base resistance does not matter in the cutoff frequency Ft, but it matters very much in your oscillation frequency Fmax. So what I am showing you here is that if you take the distributed nature of the base, then you get an expression something like that. So this represents the sheet resistance of the base, and this is of course the W by L ratio that you have to multiply. 1 by 12 the factor comes in because you have base feeding in from two sides. This is the first base, this is the second base. So base is feeding from both sides, that is why 1 by 12. If there was a single base, it would be 1 by 6. Okay. So this is the intrinsic base resistance here, and then there is an extrinsic base resistance that is given by this. Okay, SBE here is the spacing between the base and the emitter. This is the extrinsic part, so that matters that comes here. Okay, LE is the, so if you look from the top, if I have the emitter something like that, then this is your LE, the length of the emitter, and this is your width of the emitter. So typically the width of the emitter will be, it's basically the nomenclature is that you have a certain process. Say if you say 0.13 micron by CMOS process, it means that your width of the finger is actually 0.13 micron or 130 nanometer. Okay, and so on this number the circuit designer does not have much control. You have to choose a different node like a 90 nanometer, 130 nanometer. So this is not so much of a design parameter to the circuit designer. What he has control on is the length. What is the length you can use in your circuit design, and the foundry will basically give you a range of length between so and so nanometer to so and so. So for instance it could be 0.5 micron to maybe 10 micron that you can choose from. You can also choose the number of emitter fingers that you have, but again you do not typically choose beyond 2 or maximum 3 fingers. Okay. So typical emitter width, it says is 2 to 3 micron, is actually a little bit old, 15 years perhaps older. In silicon germanium or even compound semiconductor, you very much have 0.13 micron 90 nanometer nodes. I mean, you would not say nodes, because for a silicon germanium you would be basically tagging along in a CMOS foundry, so you can call it node. But in compound semiconductor, yes, you can go down really small, sub-micron, and that is how things are. Now this W that you have here, of course, this W cannot be much large, it is typically 0.13 micron or even less, or sub-micron for instance. Why don't you have 200 micron? What I mean is that if I look at the emitter finger, what if I have a giant emitter finger, something like that, this is for instance 200 micron and this is for instance 1 millimeter. Can we have an emitter pad like that? It is not realistic, I mean in the sense that it will not lead to a working device or a good device because of many reasons. You cannot have such a giant emitter pad. Typically you have to understand that these HBTs or silicon germanium BJT HBTs are actually for high frequency RF application, and such giant pads will introduce massive capacitances that will kill your cutoff frequencies, point number 1. Point number 2 is that you will have a lot of current crowding effect. The base has to push carriers from the side, so it's such a giant pad. You will have an enormous current crowding that also is very, very detrimental to the device. And of course, you cannot have 1 millimeter. Your RF signal that propagates, your frequency or the wavelength of the signal will be comparable or even less than this. So then you will have lots of phase incoherence, and you have no gain in the device. Okay, so this typically the emitter fingers are very tiny. Okay, that's how it is. All right, so then we come to the quickly again. This is a little bit of a standard fabrication approach for a compound semiconductor HBT. More recent and advanced HBT, compound semiconductor HBT fabrication processes are fairly complicated and much more elaborate with a lot of masks, but the basic premise remains the same. So we'll only go through the basics. Okay, we're not going to discuss about in the more advanced, because the fabrication of compound semiconductor HBT itself can be a course. It's very vast, just like silicon germanium or silicon BJT fabrication can be very vast. So in compound semiconductor, if you take a gas, N-gas or L-gas, or indium phosphide based HBT that we discussed, the first thing people typically do is that they put a thick, a few hundred 700 nanometer silicon dioxide, and on top of that they actually put aluminum metal, which is also very thick. It's 1.5 micron aluminum metal, which they do lift off. In compound semiconductor fabs, people allow lift off, and so you do. What is lift off? Essentially, you have a wafer, for instance. It's the side view of the wafer. You have photoresist. Photoresistance is like an organic compound, and then you blanket deposit metal by sputtering or e-beam evaporation. So the metal will be everywhere. So like that. Maybe I can use a different color. Okay, this is the metal. It's evaporated everywhere, right? It's evaporated everywhere. So evaporated everywhere. Then what you do is that you put this material, this wafer in a particular chemical solvent, which will essentially lift this off. This photoresist will get dissolved and it will be basically lifted off. So what you remain is essentially you have just a block like that. Okay, so that's called the metal block. Everything else is removed. So that's your lift off process. So you put 1.5 micron of aluminum metal on top of silicon dioxide. Why is that done? Essentially, this is done to prepare the sample or the wafer for the next step, which is isolation. So device to device, you need isolation. So people, how they isolate is that they do some ion implantation. So suppose I have an active area like that, where I will have an emitter, I will have a base, collector, etc. Another device is here, emitter, base, collector, etc. So you need to separate the two devices electrically. They should not communicate. So you, in general, in FETs, for instance, you do a mesa etching often, but here you can actually do an implant. It can be a proton or an oxygen implant, and you will basically make this area where you implant, you make it insulating, so that this device number 1 and this device number 2 cannot have a crosstalk. They cannot communicate to each other. Okay, so this implantation is done to separate the devices, and for this implantation you need a mask. So the mask is your SiO2 actually. That's the mask. This part is where you do not have the SiO2 mask. This part is where you have the SiO2 mask, but then you have to do some RI etching, reactive ion etching, to remove the layer subsequently and all. The aluminum essentially is to protect the silicon dioxide below. The aluminum metal is used to protect the silicon dioxide below, and silicon dioxide itself is used as a mask. So that is the reason we have this thing. Then do a shallow etch, and then why shallow etch? Of course, because your layers are thin, by the way, and you have to remove this from the active region. You have to remove this. This defines the active region, by the way, this blocks that I told. Then you have to blanket remove all this aluminum metal and silicon dioxide from everywhere. So do you expose the fresh wafer below. You have the gallium arsenide or in-gas. Typically indium gallium arsenide is the top layer, because it's a lower band gap, it can be highly doped, and it makes a good contact, an n-type contact to the emitter. Okay, so that's why you have indium gallium arsenide. So you essentially, if you have a wafer like that, if I look from the top, a wafer looks like that, for instance, then using the silicon dioxide and aluminum metal mask, I have defined areas where the active devices will come, and in between everything else is isolated. Okay, so all the area between these devices, which is all these areas, you have done a proton or oxygen implantation, and those are non-conducting, so those are insulating. Essentially you have isolated the devices. Okay, so I've defined the active areas here, right? Now after you define the active area, and this is the top in gas, for instance, you need to put first you will put the emitter. Okay, then you will do the base, then you will do the collector. That's the sequence in which you fabricate compound semiconductor, and that's different from the sequence in which you fabricate silicon BJT, where you first do the base, collector, of course, and then you have the emitter at the last. So the emitter process comes at the last in silicon BJT, and you do not want to play much around with the emitter process because it is the last in BJT, silicon BJT. It can actually affect the base and the collector, that will be not so good. That is why you are not concerned about the emitter so much in the BJT, you just want it to give you a low emitter resistance and a low leakage current essentially. Okay. So now in compound semiconductor you have the first emitter process, which means you need to put down contact, and typically you have titanium aluminum as the emitter metal, but titanium tends to react with the indium of the in gas below, and that could lead to reliability issues. So there is a thin layer of tungsten that is put, a refractory metal, you know, it is a high temperature, it can withstand high temperature, it is also very less reactive. You can put tungsten metal, on top of that you put titanium aluminum, and that defines the emitter stack. This is the image. This is your titanium aluminum and tungsten. The tungsten is slightly thinner here, you see it, that depends on the etch profile and the way you etch, the wet etch, dry etch, etc. So you have a titanium aluminum on top of tungsten that defines the emitter. Of course the epitaxial stacks are all here. Then the next step is that you would have to define the base now. Okay. So you have to dry etch, or sometimes a combination of dry and wet etch, so that you etch this emitter away, you come to the base here. This is the base precisely, you can see second figure here, right. Now once you reach the base, what you do is that you blanket deposit silicon nitride, for instance. You blanket deposit silicon nitride everywhere. So you have silicon nitride just like that, okay, silicon nitride just like that. This is a thick layer, maybe a couple of 100 nanometer of silicon dioxide, silicon nitride you use. Now it is depositing conformally, which means it is depositing everywhere, on the bottom, on the side, on the top, side, top, everywhere, right, and it has a certain thickness, few 100 nanometer for instance. Now when you subject this to etching in a plasma chamber, such as a RIE, a reactive ion etch, or ICP, you know, a plasma chamber, the plasma ions will bombard perpendicularly, because that is how we have mounted the sample. There are two electrodes on both sides of the sample, cathode and the anode, and this high energy plasma will come and bombard, and they will essentially remove or etch, combination of physical chemical process, they will remove the silicon nitride from everywhere else, and it is selective etch, so it will not etch the arsenide layers below, but it will etch the silicon nitride layer completely. However, the silicon nitride is deposited on the side of the stack, of the emitter stack here, will not be removed, because the ions are bombarding vertically, not laterally, correct. So any sidewall deposition on the lateral side, you see this is the way this is preserved. This silicon nitride is not removed, because that is not in the sight, in the line of sight of the plasma ions, and hence those are preserved. So those silicon nitride, suppose you gave 300 nanometer of silicon nitride deposition, so 300 nanometer of silicon nitride will remain on the sidewall of this emitter stack. Okay. Now if you blanket deposit or metal evaporate base contact metal, and a base could be an appropriate metal to make a good contact to the p-type base, the base metal comes everywhere, correct, the base metal comes everywhere. However, this silicon nitride layer that is on the side acts like a spacer that separates the base metal. This is the base, maybe I can remove some of the annotations here. You see this is the base metal, this is the base metal, okay. The base metal, of course you can define a pattern and you can define the base metal here. It will not short to the emitter, because this spacing on the sidewall of the spacer, the silicon nitride thickness that you have put down, which defines the spacer sidewall thickness, will dictate the spacing between the emitter, which is this, and the base, which is this and this. So the emitter to base distance is actually defined by the silicon nitride spacer thickness on the sidewall. So it is called a self-aligned process, because you are not worried or concerned about the base metal being aligned to the emitter. You see, suppose you have an emitter like that, metal like that, and you have to put the base here, for instance, and the spacing is critical on both sides, of course, right. If you have an misalignment in aligning the base, because in lithography subsequent layers have to be aligned to the layer below, before that, or maybe to the first layer. So if there is a misalignment, you know what will happen is that you can have alignment errors, and that can completely kill your device. Maybe you have an alignment error this side, so what will happen is that the base has come this side, this base has gone that side. So this emitter base spacing has increased a lot, this emitter base spacing has decreased a lot, that is not good for the device. In worst case it can even metallically short, because your alignment error is high. This problem is avoided by this so called self-aligned process. In self-aligned process, the sidewall thickness of the silicon nitride, this, will alone determine the spacing between the emitter metal and the base metal that you put here. Imagine that you have basically etched the silicon nitride everywhere else, but you could not etch it on the sidewall. So you have exposed the complete wafer, and now you have silicon nitride on the sidewall. Now if you blanket deposit base metal will deposit everywhere except the sidewall. So the base metal can be later patterned and etched away from any region near the emitter. However, the emitter to base distance is dictated by the sidewall. So this self-aligned approach gives you no issue, no error or alignment. Okay. So this is how they do it, and after that of course they will put a collector, they will define the collector, etch the base region to reach the collector, then they will put the collector metal. The collector metal could be, again it's an N region, so collector metal could be something like gold germanium alloy, nickel gold alloy, and you anneal it at certain temperature at certain time to make a better contact. Then you have to planarize the device. What is planarization? They have to be at the similar level. Okay. If you want to do on wafer probing, for instance, you definitely need a planar, even otherwise a planar process is good. So people do a polyamide spin coating, it's like a very dense dielectric that sticks very well, and it kind of, sometimes people also use something called BCB or polyamide. It will help you, and you can spin coat at very at high speeds, and you can do some thermal treatment, and you can planarize. It's a planar, it's all the contacts are in the same plane. Then you can define via holes, the contact holes where you can actually probe the pads, and that's it, and you deposit tie gold to make the contacts to the pad, and that concludes your basic 3-5 HBT process. But again, this is a very basic process. Advanced HBTs have very complicated process because you have many more steps when you go deep submicron record breaking compound semiconductor HBTs. Okay. So then with HBTs being over, now we have to move to silicon germanium HBT, although in some textbooks they do not call them HBT because technically it is a silicon and a silicon germanium base. This is the base actually, and this base is often graded, which means the germanium concentration is graded across the depth or the thickness of the base, and this is adopted, this is a routine practice. And so silicon germanium HBT is also often called graded base BJT. It's not technically like a compound semiconductor base heterojunction, it's a heterojunction between silicon germanium base. So here we will talk about the different parasitics such as the emitter resistance, the base resistances, the collector resistances. Then we will talk about different junction capacitances. Okay, we will look at the schematic, and we will talk about the graded base silicon germanium HBT also. Okay. So this image may look a little bit busy, but again I'll get to a more clear looking picture in the next slide. But what I'm going to tell you here is that silicon germanium based HBT is a fairly more complicated than a normal silicon BJT. There is a bit of more things involved here, and modern silicon germanium HBTs, which are very much used in BiCMOS process, again I'll come to that, are very scaled and very complicated processing. We are not going to discuss the fabrication flow as much, but the basic underlying structure should be clear, the basic underlying. So what you see here is that there is a silicon germanium p-dope base here, okay, and maybe I can use a red color font here. And then what you see here is that there is an emitter. This emitter actually, polysilicon itself can be an emitter. You see this polysilicon can itself be an emitter. The emitter and the base, they have an oxide spacer. This, can you see that? There is an oxide spacer. There could be a nitride spacer to separate out this polysilicon emitter from this black thing. This black thing is actually a polysilicon, but which is p-type polysilicon. The emitter is an n-type polysilicon. This is a p-type polysilicon. This is a p-type polysilicon, this black one, which is like a ledge. It's forming a contact to the p-type. It's forming a contact to the p-type base below. So essentially, you have a p-type silicon germanium, which is the intrinsic silicon germanium, but you have a p-type p plus poly that comes and forms a contact here. On top of that, you have metal. Okay, so there's a p-type. So it basically defines the extrinsic part of the base, that defines the extrinsic part of the base. So that's the external base. It's making a contact to the base here. Okay, essentially because it's very scaled laterally as well as vertically, it's very difficult, almost impossible to make a direct contact to the p-type silicon germanium. So you have to have this p-type poly that will enable you to make a contact to this. Okay. STI stands for shallow trans isolation. It's basically to separate the base and the collector. Okay, this is the collector, this is the base, and it also helps improve or reduce the base collector junction capacitance because this is a thick shallow trans isolation that separates the base and the collector. So the junction capacitance is also lower. Okay, the collector is typically lightly doped. So this part is a lightly doped collector. However, this part, this central part, it cannot be super lightly doped because of the Kirk effect. You need to certain dope level, and in silicon BJT we used to call them pedestal collector, but here in the parlance of silicon germanium people typically call it SiC or selectively implanted collector. So it is a selectively implanted collector, which means the n-type doping is selectively implanted there. You want it to be reasonably high to prevent Kirk effect very soon, but you do not want to be super high the doping, otherwise your breakdown voltages will suffer. Okay. And then you have a sinker. This is a highly doped N plus region, so that the collector, this is the collector contact, has a very low resistance path. It is a highly doped sinker region. So the collector contact has a very low contact resistance path here, and then it spreads laterally the collector resistance, and this is the collector, the intrinsic collector here. Okay, and the substrate comes here, right. All right, and then this is the DTI, which is the deep trans isolation. This is a polysilicon filled deep trans isolation with field oxide surrounding it. It isolates device to device, sometimes it isolates even circuit to circuit. It also helps reduce the substrate coupling to the capacitance and so on and so forth. Okay. The point to note here is that also there is an oxide, the oxide spacer is there that separates this p-type silicon, p-type polysilicon, this p-type polysilicon, and there is an emitter here, correct, like that polysilicon emitter. So this separation is an oxide spacer. Okay, this separation is an oxide spacer, we have to keep that in mind. And of course the circuit diagram looks like something like that. There is an emitter resistance, base resistance, and collector resistance. This is the collector resistance here. This resistance you can club it here itself. Okay, and then there is a base emitter diode, there is a base collector diode, and then the collector may couple to the substrate, that diode. Okay, so this is the substrate contact. So this is the basic layout of a silicon germanium HBT, except that there are many more complicated things about it. For instance, here silicon germanium actually is epitaxially grown using a specific or a special chemical vapor deposition method during the process of fabrication. So you are in the process of fabrication, and then in between that process the silicon germanium epitaxial layer deposition or growth comes. It is not like you deposited early on in the process. Okay. So this is a more colorful picture that I picked up from this company's website, IHP in Germany. So you can see the same things that I talked about in the last slide, but here it is more colorful, so hopefully you can correlate better here. The base as well as the emitter or collector, whatever, they always have a silicide on top. This thin layer you see, it could be some metal silicide layer, and the objective of this is to reduce the resistance, because silicides can have very low resistance, sheet resistance. So compared to polysilicon, if you put silicide, in combination of polysilicon, it helps reduce the overall sheet resistance of the base metal stack or emitter stack, for instance. Okay, right. So this is your polysilicon emitter. This, of course it says polysilicon emitter. You can see this blue one here. The red one, this red one is actually the base here. You can see that this is a silicon germanium base, and this is your extrinsic, this light reddish pinkish block that you are saying is actually your P plus polysilicon, which is making a contact to the sidewall, to the side of the p-type base. Okay, and this white one is basically your spacer, you can say, and then of course this orange one could also be spacer. There could be silicon nitride spacer, there could be oxide spacer. Okay, this is your lightly doped collector that also helps improve the base collector capacitance and improves the base collector breakdown voltage. This is your pedestal collector or the selectively implanted SiC collector with reasonable doping to prevent the onset of Kirk effect early on. This is your shallow trans isolation. This is your deep trans isolation to separate device to device. Okay, this is again shallow trans isolation. This is your sinker. This part is your sinker to the collector. This is a subcollector which is N plus dope. This is a buried subcollector. This is the substrate. Okay, so everything we have covered. So this is how the structure looks like. Maybe I can show you a more even better 3D schematic, and this is from another website I have picked up. You can see that this is the emitter. The polysilicon itself can be the emitter, but there could be an N-type layer below that. This is your p-type base, you can see, and this is your p-type polysilicon that is making a contact to the p-type base. The base metal will come and sit on the p-type polysilicon. As you can see, this is a single sided base contact, which means there is only contact from one side. Sometimes there could be contact from both sides. This is the collector, and of course these are all tungsten via, and the collector, this is a sinker region will come here, then this is the side spreading here. This is the STI, the shallow trans isolation, and this part could be your the small lightly doped collector region over here. Okay, and this is of course polysilicon here, deep trans isolation, and this is oxide, field oxide, SiO2. So this is deep deep trans isolation. This is dielectric. You can see this is a copper metal. Copper metal is being increasingly used in CMOS processes also. You need to make sure that the copper doesn't diffuse, so there are appropriate diffusion barriers that are incorporated to make sure copper doesn't diffuse into the active layer. As you can see, this in CMOS like processes, you have to stack the metal on top. As you keep increasing the metal the number, you are bringing the current to the top, so it makes it more compact. You have very dense, and these are all called back end of the line BOL process. Different interconnects that run crisscross, parallel, perpendicular. The way you bring them up through tungsten plug, titanium nitride adhesion, etc., and you try to bring the current up. That all these processes of metal layers, metal interconnects constitute the back end of the line BOL. Okay, but this is how again the structure of a silicon germanium HBT looks like. Okay, and after this, what we are going to do is that we'll start in the next lecture, where we'll talk about more details about the silicon germanium, the graded base, the concept of graded base, and the extrinsic resistances in the silicon germanium HBT. But today I think we can conclude today's lecture where we introduce the schematic of silicon germanium HBT. Okay, and we concluded the discussion on compound semiconductor HBT. So thank you for your time. I'll see you in lecture 49 next. Thank you.